Good morning, students. Welcome back to Signals and System online video lecture series. In this class, I'm going to cover the two topics: signal transmission through the LTI system. LTI stands for Linear Time Invariant System. We have discussed in the first unit. And the another topic I'm going to cover in this video, that is ideal and the practical filter. Filter is an electronic circuit which removes the unwanted signals and allows the desired signal at the output side. So we are about to close the third unit, and the fourth unit about the discrete time signal analysis, and the fifth unit about the Z transforms only. So we are going to discuss the signal transmission through the LTI system. We know that a system which is a linear and the time invariant is called the linear time invariant system. In addition to the linearity, if input and output characteristics do not change with time, is called the linear time invariant system. Anyway, all these things we have discussed in the first unit. We have studied the various types of systems in the first unit, such as linear time invariant systems, causal system, non-causal system, static system, dynamic systems. So we have studied the various types of systems. Now, by taking the one particular system, that is a linear time invariant system, we have to study the signal transmission through that particular LTI system. So after that, I am going to explain the ideal and the practical filter. Filter is an electronic circuit which attenuate the unwanted signals and allows the desired signals to the output side. So in this class, I am going to explain the signal transmission and the filtering. So two topics combinedly I am going to explain: signal transmission and filtering. We know that a system is nothing but it is an entity that acts an input signal and transforms into the output signal. The two most important attributes of the systems are the linearity and the time invariant. If a system is linear as well as time invariant, then that system is named as LTI system. A system which is both linear and the time invariant is called the LTI system. That is nothing but the linear time invariant system. I'm going to cover the topics here: a response of the linear time invariant system. And when the signal transmitted through that particular linear time invariant system, we have to study the distortion in the signal, and we have to study the transmission loss in the decibels we have to study. And the next one I'm going to cover, that is filters and the filtering, various types of filter, ideal and the practical filters we have to study. Quadrature filters and the Hilbert transforms we have to study. This Hilbert transform is very important in the examination point of view. And the last one, we have to study the correlation and the spectral density. In the last semester, we have discussed the probability theory and the stochastic processes, in which we have studied the correlation of the two signals and the power spectral density of the signals. Anyway, I'm going to talk about all these 6 points or 6 topics in this particular video lecture. Then I'm going to discuss about the response of LTI system. As I said just now, a system which is both linear and the time invariant, then that system is called as the LTI system. A system which is linear but time invariant, like a system which is linear and as well as it is called the time invariant. That means what? If we give the time shift in the input signal, if the same time shift followed in the output also, then that system is named as it is a time invariant system. So coming to the linearity, if a system satisfies the superposition and the homogeneity functions, homogeneity properties, then we can call that system is called as a linear system. So here we need to go for the complete system that is about LTI system. We can call it is a linear time invariant system. A system is with the linearity and as well as time invariant, then that system is named as it is a linear time invariant system. So by giving the input signal to that particular linear time invariant system, we have to study its response. Response is also called as output. But here the mentioned is impulse response. Impulse response is nothing but we have to give the input signal, that is a continuous impulse signal, so that to the LTI system, so that LTI system is going to operate on that particular impulse signal, so that it is going to give the output. That output is named as impulse response. It is called as impulse response. Then we have to study the transfer functions and the frequency response. Transfer function is always defines the, it is the plot between the input versus output, transfer functions. And the frequency response is nothing but it is a plot between the frequency and the magnitude. If we change, this is also called as the phase spectrum also, that is a plot between the frequency, that is the angular frequency versus the magnitude, that is called the frequency response. Then the block diagram analysis we are going to cover in this one. Then impulse response. Just now I have explained impulse response and the superpositional integral. Here this is a system. Assume that system is an entity which acts an input signal, so that this system is going to transfer the signal. That means the input signal get inside the system, so that input signal may undergo with the many manipulations inside the system such that it delivers the new output signal which is not equals to the input signal. So now this is a system. Simply assume that this is a system to which we have applied the XFT. It is a continuous time signal and it is a system, and we are getting the output is also y of t, that is also a continuous time system. Even though both are the continuous time in nature, but x of t is not equals to y of t. If x of t is equals to y of t, there is no meaning of having the system over here. Now we can have the output y of t, then the forced response due to the entirely to x of t. So now y of t is nothing but some force is applied. Some force is applied on the x of t. That force is defines the what function has to be carried, what the function has to be carried on the x of t within the system to provide the y of t. Then where f of x of t stands for the functional relationship between the input and output. Y of t is the output signal. How we got the output signal? By applying some operations on x of t, then we got that y of t. These operations has been applying inside the system, and so that this function relationship is also named as transfer function. F is also called as transfer function. That means what? X of t has been transferring to the y of t, has been converting into the y of t by making use of this functional relationship. So where f of x of t stands for the functional relationship between the input and output. Then what is the meaning of LTI system? Just now I have explained the LTI system. LTI system is nothing but a system which is a linear as well as time invariant. Then that system is called as it is a LTI system. We can call it is a linear time invariant system. A system which is linear as well as time invariant is called a linear time invariant system. In addition, in other words, we can say that in addition to the linearity, if input and output characteristics does not change with the time, is called as a LTI system. That is about the linear time invariant system. The linear property means that the system equation obeys the principle of the superposition and the homogeneity also. Now, if we have x of t is equals to this is the continuous time signal, assume that or a discrete continuous time signal x of t is equal to sigma k a k x of k of t. So you can take k is equals to 0 to infinity also. K is equals to 0 to infinity at any value that is satisfying this condition. So that here we can assume this is the x of t, where ak are the constant. Then y of t we can have y of t is equals to what? This sigma k is equals to, you can take some values also. K is equals to 0 to infinity, or the k is equals to minus infinity to plus infinity ak. Then this is y of t, right? How can we get the y of t? By applying the transfer function on the x of t. X of t is nothing but this is only, so that we can get this is about y of t. This is called as linearity. Then we are going with the time invariant system. Time invariant system, time invariant, that means not, if we give the time shift in the inputs, if the same time shift follows in the output also, that system is named as, it is a time invariant system. The time invariance property means that the system characteristics remains fixed with the time. Thus the time shifted input x of t minus t minus some, this is delay, we can call this is td, produces the same time delay in the output. Simple thing. If you introduce the delay in the input signal, the same delay if followed in the output also, then that system is named as, it is a time invariant system. So here by seeing this one, you can come to, you should come to a conclusion that here f of x of t minus d, that means what, earlier what we have, it is for a transfer function applied on x of t only, but here we are giving some time shift, that is t minus td. It is a time delay we can assume. That means what, we have been introducing some delay in the input signal, so that the same delay has been following that the output side also. That means what, the output is time shifted, but otherwise it is also called as unchanged. It is unchanged. So now it is a direct analysis of a lumped parameter system, starting with the element equation leads to the input output relation as a linear differential equation in the form. Lumped parameter system also we have discussed in the first unit. That means what, if you wanted to calculate the response of a system, if that response is belonging to some components which are lumped together, which are very closest together, then that system is named as, it is called a lumped parameter system. So obviously lumped parameter system, in the lumped parameter system analysis, we can have the some linear differential equation, that is an dn y of t by d to the power dt of n. Like that we can have this this linear differential equation. We know that this first order and second order linear differential equations also there. So that this, unfortunately this equation doesn't provide a direct expression for y of t. See this one, every y of t is associated with some d of t, d of t, d of t, but we require to have the y of t only, because output of any system is described with the y of t only. This is y of t is nothing but, it is some functional relationship applied on x of t, and here this is x of t, here what differentiation, that y of t is associated with the differentiation, so that unfortunately this equation doesn't provides us with the direct expression for y of t. To explain, to obtain our explicit input-output relation, we must find that we must first define the system's impulse response. System's impulse response, it is very clear. System's impulse response is denoted with the h of t. H of t. How can we get the impulse response? By applying the impulse signal as an input for a system. By applying the impulse signal as a system, so that on this signal some transfer function has been applying. On this system some transfer function has been applying, so that we can get the output, that is h of t. H of t is nothing but, it is an impulse response function. So now here we have been using, in place of x of t, it is a input signal. In place of x of t, what we are taking, it is a impulse signal we have taking, by applying the impulse signal we have been getting the output, that is a response, that is called as impulse response function. So that h of t is nothing but it is a impulse response function that is about del of t. That is h of t by applying the impulse signal, that is del of t. Here del of t we have discussed in the first unit, that is nothing but it is a continuous time impulse signal or the function which can have the amplitude t is equals to 1, which can have the amplitude of 1 at t is equals to 0, and it can have the amplitude of 0 and the remaining values of t except t is equals to 0. So now we are having this is about the continuous time. If any continuous input signal we can return in the convolution form. This thing we have studied in the third unit, that is the properties of the convolution also. So now we are going with the convolution. Now we can write the convolution of x of t. This is a input signal, that is x of t is equals to x of t in convolution with the impulse signal, that is del of t. So we can have the y of t. If this is the input signal, if this is the input signal for the system, then what will be its output? Then y of t is equal to, y of t is equals to y of t is equals to some transfer function applied on that particular input signal. That convolution can be written like this: t can be replaced by the delta, and this del of t can be replaced by the t minus lambda. So now this is nothing but it is the convolution property. This is a convolution property. Anyway, we have discussed this is in the third unit. So that integral minus infinity to plus infinite x of lambda, in place of t we are taking the dummy variable, that is the lambda, into del of t minus it is delayed with the lambda into we have going with the integration, that is with the d lambda. So now we can go with the integral minus infinity to plus infinity, then x of lambda I am taking out, so that this is the forced function applied, transfer function applied on del of t minus lambda into d lambda. So now this is nothing but this is what it is, the input, it is the input applied to a system, that is the impulse signal which is having the delay of lambda, which is having the delay of lambda. So from the time invariance property we can have, that means what we have the input signal, that is the input signal is what, del of t minus lambda. This input signal we have been applying for the time invariant system, so that output will be h of t minus lambda. We know that if we apply del of t, if we apply the del of t, then we can get the output is about, we can get the output is h of t. But in place of del of t, what we are applying? In place of del of t, we are applying t minus lambda. In place of del of t, we are applying the del of t minus lambda, such that here we can get the h of t minus lambda. Here we can get the output is also h of t minus lambda. See this one, h of t minus lambda. So that y of t is equals to integral minus infinity to plus infinity x of lambda into this is nothing but it is the impulse response. It is the impulse response of a time invariant system if the impulse signal at the input side is delayed by the lambda units. So that this is nothing but it is the impulse response of that time invariant system. So that we can have the y of t is equals to, we can have the y of t is equals to integral minus infinity to plus infinity h of lambda into h of lambda into, I can replace this one is what, h of lambda. I am replacing this two terms, so that by making use of the convolution property I can replace this independent variable h of lambda and the x of t minus lambda. This is possible with the convolution theorem, so that we have interchanged the independent variable in the x signal and as well as impulse response of time invariant system. So that then we can have various techniques exist for the determining the h of t. Now we have to calculate the h of t from the differential equation or some other system model. Now we are going with the one function. However, you may be more comfortable taking x of t is equals to y of t and the calculating the system step response. Now I am going with the system step response. I can denote with the g of t, because we know that unit step function, that is u of t is for 1 for the t greater than or is equals to 0, and the 0 for t less than 0, so that it is called unit step response. It is a unit step response. Del of t, g of t is nothing but it is a unit step response by applying the unit step signal as the input for the system, such that you can get the g of t, and such that you can write here h of t is equals to h of t we can get, that is a impulse response of a unit impulse signal by differentiating that system's step response with respect to the time, so that you can get h of t, so that you can replace that y with the h of t is equals to d by dt of g of t, and by having this particular thing we can find the time response of the first order system. Now you can go with the one RC circuit, that is what here this is a R, and it is a R is nothing but resistor. Resistor is a passive component which opposes the flow of current, and whereas C is nothing but it is a passive element. It is a capacitor which stores the energy in the form of y of t. It stores the energy in the form of voltage, to which we have been applying x of t. X of t may be anything, that may be any continuous time signal, that is an analog signal we have been applying, so that thus continuous time signal is applied to the RC circuit, that is a first order RC system. That is, this is a resistor, units of the resistor is ohms, and the units of the capacitance about the farads, so that we have to examine what will be the y of t. That means what, we have to examine the output, or we have to examine the time response of the first order system. This circuit is a first order system governed by the differential equations. We can have this is about RC. This is a RC, sometimes you may call as a time constant. RC is equals to dy of t by dt plus y of t is equals to x of t by, we require to get the y of t, what exactly the y of t is only. Here y of t is there, and again y of t is associated with some other differential function, such that it is difficult to analyze what exactly the y of t is from the either the differential equation or the circuit diagram, the step response. That step response just now I have explained. The response we got from the system by applying the unit step signal as input, so that we can got g of t is equals to 1 minus e to the power of minus t by RC into u of t. This is about, it is nothing but it is a unit step response from the first order differential equation. By plotting this thing g of t versus t by taking the various values of t, you can get the slope of that particular g of t is like this, such that the corresponding impulse response also you can go with the h of t is equals to 1 by RC into e to the power of minus t by RC into u of t. This is about the corresponding impulse response, that is h of t versus t, and like that you can go with the two plots. One is about it is a plot between the unit step response to the time, and it is a plot between the impulse response to the time. Anyway, all these things are not needed for your signals and system. You require to have what exactly the impulse response and what is time invariant system only. And this one is about the impulse response with respect to the time, and such that this is convolution. Just now I have explained convolution. Y of t is nothing but it is the impulse response in convolution with the x of t, and such that it can be divided with the three parts by taking the t less than 0, and by taking the t is positive, by taking the t is a negative, we can have y of t is equals to 3 part. Based on those 3 parts you can plot all these things. That means for the negative, for the positive, for the remaining things also you can do. Then transfer functions and the frequency response. I am going to explain the transfer functions and the frequency response of that LTI system. Transfer function just now I have explained. It is a relation between the input and output and such that we can find the relation between the input signal and the output signal. For example, if we are having the input signal is about unit impulse signal, that is del of t, and the response of that particular unit impulse signal from a system, we can call it is a unit impulse response, that denoted with the del of t. If you find the relation between x of t and the del of t, that will be called as the transfer functions and the frequency response. Now I'm going with the time domain analysis becomes increasingly difficult, and higher order systems we got a clear view of the system response by doing the frequency domain. Then we are having this thing I have explained in the starting of the third unit, that is the continuous time signal analysis. If we analyze a signal, when that is there in the time domain, it is very difficult to analyze. When we convert the time domain signal into the frequency domain, it will offer the ease of analysis, and we can easily analyze that signal, and the frequency domain can be applied for the periodic signals and the aperiodic signals also. All these things we have discussed in the beginning of the third unit. So now I am going with as a first step in the direction, we define the transfer function. Transfer function is nothing but the operation which is going to applied on the input signal inside the system, and that is called as transfer function. How the signal has been transferring from the one type of signal into another type of signal, that is called transfer function. As a first step in the direction, we define the system. Transfer function is to be Fourier transform. We know that the Fourier transform is nothing but it is a mathematical tool which is used to convert the time domain signal into the frequency domain signal. Now we are going to have that is a transfer function h of f. F is nothing but it is a frequency. You can mention this in place of f, that angular frequency omega also. That is nothing but h of f is equals to some function applied on h of t. H of t, we know that it is the impulse response. This is the output from a system whose input is the impulse signal, that is del of t. Now on which we will be applying the Fourier transform. We know that the Fourier transform operation, that is integral minus infinity to plus infinity, and this is about, now we can call it is x of t, and x of t is, we can have the h of t into e to the power of minus j 2 pi minus j 2 pi ft, and in place of 2 pi ft you can make use the omega also, and with respect to the dt we have been getting the simple point. You have to remember that transfer function is nothing but applying the Fourier transform on the impulse response. H of t is nothing but it is the impulse response. It is nothing but output of the system, output or the response of a system whose input is impulse signal. That means here free transfer function is nothing but applying the Fourier transform on the impulse response of a system. Here this definitions requires the HF exists. We have studied this is the Dirichlet condition. It requires to have the finite value. This integration must be finite value, and requires to have the minimum and the maximum value. It requires to have the continuous discontinuities. All these things we have studied in the Dirichlet conditions. That means conditions for existence of the Fourier transform of x of t. Here the x of t is nothing but it is a impulse response, that is h of t, and the three conditions I have explained in the beginning of the Fourier transform, that is the continuous time signal analysis, in which that is the three conditions are there. That three conditions combinedly we can call it is a Dirichlet conditions, or the conditions for existence of the Fourier transform. Now we can have this h of f is nothing but what? It is a frequency domain signal. It is a frequency domain signal by applying the Fourier transform on x of t. It is nothing but it is the x of t is nothing but it is a impulse response on which we applied the Fourier transform, and so that h of t is a real time function. H of f has the Hermitian asymmetry, that is nothing but it is the complex function. We can have the j function also, that is a j omega function. It is the real part and the imaginary part, both we will have in that the frequency domain signal. So that h of minus f is equals to h convolution of f, and we can replace this one here also. You can get h star of f. Star indicates it is a convolution symbol, so that you can go with this representation. H modulus of h of minus f is equals to, we know that modulus of h of f. In place of f you can take the minus omega also. If it is replaced by minus omega, you can replace this by plus omega, and like that this is nothing but magnitude of x of minus omega is equals to magnitude of x of omega. Angle of x of omega, h of omega is nothing but minus angle of x of omega. This thing also we have studied in the Fourier transform, that is in the case of phase spectrum and the amplitude spectrum. All these things we have studied. This is a steady state forced response. Steady state forced response y of t is equals to integral minus infinity to plus infinity del of t. Here we have the x of t. In place of x of t we have this one. If you simplify, you can get this of h of f naught. This is a dummy frequency variable. Like that, if you go through this derivation, you will get the final answer for the y of t. Y of t is nothing but the output from the system whose response, whose input signal is the impulse signal. Output is called as, it is the impulse response. Then in the coming class I am going to explain about the filter circuits. And this is, we have studied the amplitude and the phase shift. All these things we have studied in the first unit, in the beginning of the third unit only, so that we can have this y of t is equals to, now we can have the y of t is equals to y of t is the input signal which is applied to the time invariant system, so that we got the y of f is equals to here h of f into x of f. We can have this is from the linear time invariant system. We have to prove this one. Y of f is equals to h of f into x of f. Like that, you can go with the energy signals and the power signals also, that I have explained in the first unit. So in the next class I am going to cover some filters. These are the best examples, and you can go through all these things. Anyway, I am going to share the syllabus. I am going to share the material of this one, and the next class I am going to explain. Next class I am going to explain the ideal and the practical filters, and with that almost the third unit is going to be completed successfully. So students, try to write the notes from all the shared videos from all the subjects, such that you will be ready for the preparation. You will be ready with your material for the preparation for the external and the second mid theory examinations also. Thank you students. Thank you so much.